In this screencast, we will look at solving material balances for a two-phase reactor that has a desired reaction and an undesired side reaction. We're going to examine the process of making chlorobenzene, which is commonly used as an intermediate compound in the manufacturing of herbicides and rubber, as well as being a common high-boiling solvent that's used in industry and labs. It is synthesized catalytically by the chlorination of benzene, as you can see here in this first reaction. Now, a side reaction occurs that cogenerates dichlorobenzene. This is our undesired product. So we're told that liquid and gas streams enter and leave the reactor, and the reactor is operated at 130 kilopascals and 45 degrees Celsius. Now, pure species are fed, so we have a pure benzene liquid feed and a pure gaseous chlorine feed. So the exiting liquid stream has the following composition given to you in weight percents, and the exiting gas stream has a different composition given to you in volume percents. So our job is to size the separation units that maybe follow this reactor, but first, before we do that and continue to design our process, we need to know the selectivity of the desired and undesired products, so we have some idea of what's going into downstream processing, as well as the volume of gas per kilogram of benzene used that comes out. We have a good old-fashioned material balance problem, and we need to go through our steps in solving this. So the first thing to do is draw a nice schematic and label everything we know about our streams. So here I've drawn a little schematic that shows our liquid feed of 100 weight percent benzene coming in and our gas feed of 100 weight percent chlorine. We have our two reactions and the outlet streams labeled using the appropriate information given in the problem statement. So the next thing is to label our unknowns. We don't know the flow rate of our benzene here, which we'll call stream 1. We also don't have any information about the flow rate of our chlorine stream or our exiting stream. So I've given those the unknown variables M1, M2, M3, and M4. We know everything about the composition of these streams. We don't know anything about the yield, selectivity, conversion, or anything regarding these two reactions. Now the next step, we want to perform a degree of freedom analysis to examine this problem and determine if we could even solve it, or what maybe information we could plug in to solve it. So I've copied over the kind of things we need to consider in this problem for a degree of freedom analysis. So we start with the unknown labeled variables, which we had the 4 flow rates. We add any independent reactions. We have 2 independent reactions, minus any independent reactive species. We have a total of 5 species. We have none non-reactive species, and we don't have any other equations that relate these unknown variables. So this gives us a degree of freedom of 1, which means that given the information that we have, we cannot solve this problem. Now fortunately, we are looking for a ratio of the outlet products to the inlet reactants, selectivity, so we could choose a basis for this problem to use. So in this case, our last degree of freedom is going to be wiped out because we're going to choose a basis. I'm going to use 100 moles per hour of benzene entering. It's always an easy one to work with when we have compositions given as percentages or fractions. So let's first determine the mole fractions of the components to use in our material balances. Now there are different ways to approach this, either using an average mixture molecular weight and converting using that value, or a step-by-step conversion going from our mass fraction to the amount of moles, and then from the amount of moles to a mole fraction. Now whatever method you choose, you should get the following values that I've written in this table. Now I'll step you through the first one. We'll do this for benzene. So let's choose a basis of 100 grams, and this is for our mixture. Now we use the mass percentages of our mixture. We get 13.4 grams of benzene, C6H6. We repeat this for the rest of our mixture, and this is just the liquid mixture, so we have 47.4 grams of C6H5Cl, and the remaining 100 grams, which is 39.2 grams of C6H4Cl2. So now we have the amounts that we would have based on our basis, and now we divide each amount by its respective molecular weight. So for benzene, we have 13.4 grams of benzene. We divide this by the molecular weight of 78.11 grams per mole. This gives us the amount of moles that we would have. So once we have the amount of moles of benzene, we repeat this for other 2 species. And then lastly, to get the mole fraction, we just take the amount of moles of benzene and divide it by the total amount. And this gives us our mole fraction of benzene in the mixture. So I've written them as mole percentages in this column. And again, this is for the liquid mixture. For the gas mixture, now we need to assume some kind of gas law. So let's assume the ideal gas law is okay since we're operating at relatively near ambient conditions. Now that being the assumption, we know that the volume fraction is the same as the mole fraction. So I've just copied over the volume fractions into the respective mole fractions for those two species. So now that we have our mole fractions and we assumed a basis of 100 moles of benzene an hour coming in, we could write our extent of reaction equations for each species. So the idea here for an extent of reaction is that whatever comes out of our reactor is whatever comes in minus what's reacted. Or whatever comes out is whatever comes in plus what's generated. So when we do this for each species, we could calculate the extent of the reaction, or basically what's reacted or what's generated, for each of the two reactions. So let's start this out with benzene. So for benzene, we would write the moles that are leaving. This is equal to 100 moles coming in minus what's reacted. And it's only in the first reaction, so I subtract out the extent of reaction of reaction 1. So I could continue to write these for each species, but before I continue, we don't know the molar flow rate out because it wasn't given to us. But can we get it easily? Now for reactions, it's sometimes difficult to know the flow rate out if the stoichiometry isn't one-to-one and more information like conversion or yield or selectivity isn't given. However, here we have a 1 mole of liquid benzene and 1 mole of gaseous chlorine coming in to form 1 mole of liquid chlorobenzene and 1 mole of gaseous hydrochloric acid. Now the same is true for the undesired reaction. We have 1 mole of liquid and 1 mole of gas going to 1 mole of liquid and 1 mole of gas. So that means 100 moles of liquid entering gives us 100 moles of liquid leaving. So that helps us here. So now we know, based on the molar composition given to us for the outlet streams, how many moles we have leaving. So I'm going to rewrite this such that using that information, we have 20 mole percent times our 100 moles, so we have 20 moles leaving. So we can solve for the extended reaction as 80 moles per hour. So I could write this now for the next species. So for the chlorobenzene, we know that we have 49 moles that are leaving. We had nothing coming in. We generate from reaction 1 and we react from reaction 2. So our extent of reaction 1 minus our extent of reaction 2 should give us 49 moles per hour. This means that the extent of reaction 2 is 31 moles per hour. So I could also write this for dichlorobenzene. And for dichlorobenzene, it's just what comes out, which is 31 moles per hour. And this is equal to the extent of reaction 2. And we can write this for HCl as well as for the chlorine gas. Now for HCl, we produce it in reaction 1. We also produce it in reaction 2, and we don't consume anything, nothing was added. So for HCl, it's just going to be the moles out, and that's equal to the extent of reaction 1 plus the extent of reaction 2. So based on our extent of reactions, this should be 111 moles per hour. So we have 111 moles of hydrochloric acid coming out in the gas stream. Now for chlorine, we write this again, N out is equal to the extent of reaction 1, but we're consuming it, so there's a negative sign, minus the consumption in reaction 2, plus whatever we had coming in. And we don't know this value, but we did label it as N2 in our problem statement, or M2 for the mass flow rate. So fortunately, we do know N out, or we can figure out what N out is. So to determine N out of our chlorine, we know the mole percent between HCl and the chlorine gas. So we could write the N out is equal to this ratio, 9/91, times the amount of moles we have of hydrochloric acid. And this gives us about 11 moles per hour that come out for our chlorine gas. So that means N2, or what we put into the process, is going to be the 111 plus 11, and that gives us 122 moles per hour. We wanted the selectivity and the volume of the gas produced. So selectivity in our liquid stream is just the moles of our desired product over the moles of our undesired product. So if we go back to our composition, this was 49 moles of our chlorobenzene over 31 moles of our dichlorobenzene. This gives us a selectivity of about 1.6. Now for the volume of gas, we need to choose a gas law to use, and we already assumed the ideal gas law due to the near ambient reactor conditions. So using the ideal gas law, we have 122 moles of gas leaving. Now this is at a temperature of 45 degrees Celsius or 318 Kelvin. Using the appropriate gas constant, which here it's 8.314, and dividing by our pressure, we get a volume of 4.74 meters cubed, and that's per hour based on our basis. Now we wanted this on a per kilogram basis of benzene, so our volumetric flow rate divided by our mass flow rate of benzene will give us our volume per mass of benzene. Gives us 0.6 meters cubed of gas per kilogram of benzene. So for each kilogram of benzene we put into our process under these operating conditions, we would have 0.6 meters cubed of that gas going into whatever unit downstream we may have. Now this would change if the degree of each reaction changed and or the pressure and temperature settings were altered.